So welcome back to this afternoon session. So it's my pleasure to introduce again Fino, who's going to give her last lecture on balance matrix, interplays of complex and symplectic geometry, and then the subtitle for this lecture is Balance Matrix and the whole Stroming system.
Thank you very much. I want to thank again the organizer for the invitation, the kind invitation, and also the ICTP and SIM. And so in this last lecture, we will see an overview about balance metric and the whole Strominger system. And we will see again that this is the balance metric can be viewed as a sort of generalization of Calabi-Yau metric. So let's start. Let's start to define what we will mean for a balance metric. So we will have a complex manifold, complex dimension n, and the Hermitian metric. Here, for simplicity, I will identify the metric with the fundamental form, omega, that we denote in the first lecture. And we said that the metric is balanced if essentially omega is co-closed. That means that we will have n-1, n-1 form, which is positive. This type of metric was considered by Michelson. And there is also a nice characterization of Hermitian metric in terms of balance condition is due to Gudouchon. And it shows that the Hermitian metric is balanced if and only if you have this relation that relates the Hodge, the Laplacian Hodge with respect to D, with the Laplacian with respect to del bar and del. And Michelson, when defined the balance metric, was in relation to currents. In the first lecture, we saw already characterization of the existence of Keller metric and other type of metric on a compact complex manifold. In this case, the characterization for the existence of a balance metric is that M has not to admit any positive currents of degree 1, which are components of a boundary. And that is nice, there's a lot of things, we'll see some of them. And there is also an extraction for the existence of balance metric on compact complex manifold in terms of codimension 1 compact manifold, which cannot be cohomologous 0. And in particular, for instance, Calabi-Yau manifold cannot admit any balance metric, also other compact complex manifold. You can apply that abstraction to other type. But we are interested in manifold which have this type of metric. So let's see the first type of construction that preserve the existence of balance metric, and is due to essentially to this property, Alessandrini and Bassanelli. Essentially, a modification preserve the existence of balance metric. In fact, I review just what is a modification. Is a holomorphic map between two complex manifolds such that there exists a complex manifold here in N, codimension bigger than or equal than 2, and B holomorphism outside this epsilon and the pre-image given just by restriction. And that's very nice, this property shown by Alessandrini and Bassanelli, because for instance, say essentially that the B meromorphism preserve the balance condition. So one can get in an easy way balance manifold just applying a B meromorphism to Keller manifold. In particular, if you apply to projective manifold, you get the Moisson manifold that we considered already in the first lecture. And more general, if you apply meromorphism to a compact Keller manifold, you get what are called the manifold in Fujiki class C. So all of these are balanced, but there is another type of construction that is very nice, that allow to construct balance metrics starting from Calabi-Yau metric. In fact, this is a construction due to Fu, Li, and Yau, the transition, conifold transition. I will explain a little bit how it works. And it's essentially using the Clemens-Friedman construction. So the idea is the following. Here we work in dimension 6, real dimension 6, complex dimension 3. So we start with Calabi-Yau, free fall. And let's take K mutually disjoint, smooth rational curves. So we have a copy P1C with normal bundle isomorphic to O minus 1 plus O minus 1. So it's what are also called minus 1 curves. So what we can do is to contract the K rational curves. What we'll get is a singular Calabi-Yau. Here I use Calabi-Yau, but this is not always the case. In fact, you get something which is non-killer. So I reduce Calabi-Yau in more general case, just saying that you have a complex manifold of complex dimension 3 in this case, and you have holomorphic non-vanishing 304. And what we get is a singular non-killer manifold, let's say free fall, not manifold, with K ordinary, double point singularity, P1, Pk, that you take contracting. And what is going on that if you remove, let's say from M, the union of these rational curves, in fact, you get something that is bilomorphic to M0, removing the point P1, Pk, so the singularity. And the neighbor, let's say locally, what you get, a neighbor of the point in M0 is just a neighbor of the origin in this locus inside C4. This is what you get geometrically. And if you take the fundamental form associated to Cj and you view as an element as a 2-2 form, rational 2-2 form, satisfying this condition with Nj different from 0 for any j, then this is due to Friedman, Tian, and Kawata. There is a family of complex manifold MT over a disk in C. And this is in fact, so before we did a contraction, let's say, and now we are doing this smoothing. This is what we are doing. We go from M to M0, and then you construct this family. This is what is called conical transition. And what happened here, that for T different from 0, in fact, you get really a manifold, a smooth free fall. And for T small, the local model is just the locus that I described before. And the central fiber is singular, and this is actually the M0 there. And that's nice because the first remark, it's a property due to Friedman, that if you contract enough rational curves such that the A2 of MT is 0, for T different from 0, then you get what is a famous result, that the connected sum of S3, or the product of S3 times S3 for any K bigger than 2 as a complex structure. And what Fu, Li, and Yao show that for T is, let's say, sufficiently small, then the conical transition that I described quickly, MT, is a balanced matrix. And so in particular, we have this manifold, okay, the connected sum over K is bigger than equal to 2, is balanced. As far as I know, it's still open, completely open, the case K equal to 1. Okay, if we take the Calabi-Ekman structure there, you know that there are no balance, but for K equal to 1, one doesn't know
Anna,
what is going on. Yes.
Anna, excuse me. There is a question.
Oh, yes, sorry, I didn't open the chat. Let's see. Is MS0 still a Kähler space? No, not necessary. In general, it's not preserved. What is preserved in general is the Dilbert lemma, satisfy the Dilbert lemma. So it's not Kähler, but it satisfy the Dilbert lemma. I hope that's so. I use Calabi-Yau in more general part. I think about this. What I am going to talk, now I sponsor some notes of some people here. Mario Fernandez write a very nice notes about balance metric and the Hall-Strominger system. So I suggest to the people that the first time that they see that look that notes are really nice. Okay, so let's go on. So more example of balance metrics. Some of them we already saw in the first lecture, the twistor space of four-dimensional oriented anti-cell dual Riemannian manifold as a balance metric. There are very simple examples, in fact. This is due and resolved by Abel and Grassi. Just take a unimodular complex Lie group, okay? And any left invariant Hermitian metric here is automatically balanced, okay? Here for complex Lie group, I mean, this is related to a question that I received in the first lecture. So here J is really by. The complex structure J is by invariant. And then if you quotient your Lie group by lattice, you get a complex parallelizable manifold. So always are balanced. And it's nice result, I didn't know about that. I heard in another workshop that when the group is semi-simple, then the form omega n minus 1, the power form, is exact. This is strange. It's really a strange property. Usually when you have this Hermitian metric, the class defined by, let's say, this omega n minus 1 or omega and so on, easily they are not trivial in cohomology, but in this case are trivial. And then I get jointly with Grancharov and Vezzoni some characterization for compact complex homogeneous space with an invariant volume. Here I mean that you have a homogeneous space and we have essentially all the complex structure and the volume form are both invariant by the action of the complex group. That's the idea. And we characterize that, and what it turns out that the C1, the first chain class, has to be non-zero. And then there are many other results in the case of compact locally homogeneous space, for Neal manifold, due to Luis Ugarte, for Sol manifold, and so on. There are many results in the literature. So let's go back to the first lecture, right? In the first lecture, we saw many things, or some things, about pluriclose metric. Okay, so one can see the interplay with this different type of metrics. So the first thing that one can ask, so J is fixed. So we take, okay, this J, we have a complex manifold and J is fixed. So we can ask first, consider a Hermitian metric and thus together both conditions, so balance, the closure, and pluriclose condition, that was ZD bar omega 0. That's not possible unless you get Keller. This is due to independently was proved by Alessandro Ivanov, by Popovici. So we conjecture with Vezzoni that, okay, what happened? So J is fixed, and suppose that you have a balance metric, okay, in the sense that we see now, and also pluriclose metric. Okay, we conjecture that scalar. In fact, if you look, all the examples that until now they say, that doesn't mean that conjecture is true, but it's open, completely open. It's true for the twistor space, as we see in the first lecture, okay, by the result by Verbitsky, for the Fujiki class, by result by Chiose. It's true also for the manifold that I described before, constructed by Li, Fu, and Yao, essentially because they satisfy the Big-Bar lemma. And it's true for two-sapling manifold, for many types of Sol manifold. And also recently, Ottiman, in the first lecture, I described a little bit this type of manifold, the OT manifold. And also for this case, it's possible that they are non-balanced. So you have pluriclose in some case, but never balanced. So this is completely open. And there are also relations with other type of metric that one can ask. This is the Euler result that I get with Georg Grancharov and was related to a conjecture posed by Gutowski, Ivanov, and Papadopoulos. And the question was quite, let's say, natural in some sense, because let's say we're compact Hermitian manifold, we follow morpholically trivial canonical bundle. Okay, so you have a section, your zero section of the homomorph of the canonical bundle, and Bose-Bismuth Ricci tensor vanishing. And then the conjecture that was automatically scalar, this is not true. We show that this implies another condition on the metric, which is the globally conformally balanced condition. I will use also later. What does mean? You start with omega, and then there is, with a conformal change, global conformal change, we will get a new metric which is balanced. Also, one can ask the same question, as I saw before in the conjecture, combining the condition for the existence to have a balanced metric with another type of metric that I didn't talk in this lecture, but is also important, non-Kähler geometry, and is an option of a Steno-Kähler metric. That means that another power, dd bar of omega n minus 2 is 0. Okay, for n equal to 3, it means that it's just the pluriclose condition. And in this case, we were able to prove that, in fact, this is not anymore, I mean, there exists a compact complex non-Kähler manifold which admits a balance and an Atheno-Kähler metric. We constructed a simply connected example, more or less on the same time. Also, La Torre and Ugarte construct a different example. It was an in-manifold example. So that was related to some question posed by Zekeleidi, Tosati, and Vaikov. Now, before to talk about Hall-Strominger system, which is related to, in fact, to a flow that is preserving the conformal balance condition. Yes?
Excuse me, this is Adriano. Can I ask a question on the last theorem? So the example has dimension greater than 3?
Yes. The one, okay, our example, I am going to, okay, let's go here. Okay, this example that we construct is SU5 over T2, so it's for sure. And as far as I remember, the example constructed by La Torre and Luis Ugarte is also is bigger dimension. I think it was 8-dimensional, something like that.
Okay.
Yes, okay. Yes.
So complex dimension 4.
Yes. Yes. Because anyway, if you take n equal to 3, then you go back to the conjecture, right? Because you will have a balance.
Yes. Great.
Okay, and contemporary in the same time a pluriclose metric. Okay.
Yes.
Okay.
Thank you.
So in some, let's say that this is for n bigger than 3, it's some sort of generalization, but this is not anymore true. So probably that depends on the Steno-Kähler in some sense. It's maybe in higher dimension is completely different than pluriclose metric.
Yes. Okay. Thank you very much.
Okay. Okay, so now I will try to describe first, it's not so easy to evolve a balance metric preserving the condition to be balanced, right? So J is again fixed. And what introduced this flow, we'll see later another flow, the anomaly flow that's related to Hall-Strominger system. And this flow preserve a flow that in some lecture we didn't define, but was I think we talk about that, is Calabi flow, okay? That's, we will see why is related to the Calabi flow in the Kähler case. Here, what we do, so J is fixed, so we have our balance metric, omega 0. And then what we do, we not evolve omega, but we evolve omega n minus 1. So the n minus 1, n minus 1 form. And how we evolve, so phi, let's say, will be identified with that posteriori, when it's positive, define a meter metric. And we evolve our n minus 1, s minus 1 form in this way. So here is just the Ricci form, the chain associated to omega t. And here is the both chain Laplacian. So you can see that this is 4 order, okay? flow. And essentially, when it's scalar, this is not here. So it's only this part in the scalar case. And Bedoulle Vezzoni show a short time existence and uniqueness for compact manifold for this flow. And this is exactly what I was saying here, that when you start with a scalar metric, then the flow coincides with the Calabi flow. Here I write in a different way, but essentially is equivalent to the form that I wrote before. So you evolve omega t, essentially in omega 0, in the class of omega 0, in order to be positive. That was the notation that I used, C omega 0 last time. And S omega t is just a scalar curvature associated to the metric. Recently, with my student Paradiso, we looked at how the behavior of this flow, because not much is known, in fact, about this flow. And when we looked at in the Lie groups case, and when you have almost a billion Lie group, what is going on? That effect is nice behavior. The solution is defined for every t. And again, you have a Chichel-Graham of convergence. Here, one has to be careful because you are not in a company group, so it's a little bit adaptive on this situation. But anyway, you have a convergence to a scalar almost abelian group. I think it would be nice to have more results about this flow, and maybe can give also something in relation to the existence of pluriclose metrics. So combine this flow with the other flow, pluriclose flow, and see if you get something or not. Okay, so now let's go to the whole Strominger system. And this give a link with Calabi-Yau metric, we'll see. So I will try to give just a physics, few things, right? So the idea is you want to describe a compactification of heterotic superstring distortion to four-dimensional Minkowski space-time, which will be just R13. Okay, the Minkowski space, flat Minkowski space. What is a compactification? Is just a link between the 10-dimensional and the 4-dimensional. Locally, we will have a product. So we will have a product like that, M6 times R13. But the important thing here that M6 will be a compact complex manifold with a posteriori free structure. Anyway, we have a 10-dimensional Lorentzian manifold, M10, which is a product, as I say, locally a product. And then we have a vector bundle, a holomorphic vector bundle, a gauge bundle over our 6-dimensional manifold. And the idea is to reduce all the equations required by superstring theory to the geometry of the 6-dimensional manifold. In fact, we will not describe all the equations. We will describe all the equations beside the equation of motion. I will say a few words in a moment. So the metric in general, the type of metric that you have in this product, it can be a product metric or a warping metric. In fact, first was considered the case where you have a product metric. So let's consider the case where you have a product metric. And then essentially the gauge connection, let's say the holomorphic bundle is just a tangent bundle, and the gauge connection is a spin connection. And this is exactly linked because all the situation, let's say the physics situation for M6 to be Calabi-Yau with a Kähler-Ricci flat metric. And let's say the existence of that is just the Yau theorem, okay? The existence of a Kähler metric in the class of a Kähler, which is Ricci flat, is just that. And this was generalized by Strominger, considering the case of warping product metric, okay? And in this case, this is what I say already before here, we will use Calabi-Yau in more general case. So the manifold will be not necessarily Kähler, but the canonical bundle or your compact complex manifold will be trivial. Okay, so we will have a non-zero, non-vanishing holomorphic free zero form. Now let's see our equation of all Strominger system. Okay, so we will have let's say a compact complex manifold, complex dimension phi, with an aware vanishing holomorphic 0,4. And then we will have a complex vector bundle M with an Hermitian metric H along its fiber. And let's take a constant alpha prime that is exactly involving in this equation. So Hall and independently Strominger describe the physics situation in terms of this system. We have three equations. Is a system that combines, in fact, an Hermitian metric on M and Hermitian metric H on E. And the first equation, you can see here, we will see FH, that's right here. FH is just the curvature of the chain connection. So curvature chain connection on A, I call H. Okay. And we will see this like a 1-1 form with value in endomorphism of E. That's why here we can take the trace, okay, of this form. And the condition here for this condition is just the Hermitian Young-Mill. That in the Kähler case, when the manifold is Kähler, this by the result by Dolonsol, Uhlenberg, Yau is just a condition for the bundle, okay, the bundle E when it's reducible to be stable in geometric invariant theory. Roughly speaking, it means that it's more ample than any other proper subbundle. And then the second condition is that if you take your omega square and you multiply for the norm of the free zero form, here there is a mistake, sorry. This C is big omega. Okay, sorry for that. If you multiply that, so this is just a positive function, then the differential is 0. So here you can see the condition to be conformally balanced, right? Because by a factor function positive, you get a balance metric. And then the third equation, which is the more important one, which is also called Bianchi identity. And this involves exactly is the one coupling the two metric. It is some sort of curvature condition that can generalize, let's see, like the Kähler-Einstein condition, because it's a condition involving the curvature, as involving the chain connection, the curvature of the chain connection on E, FH, and the curvature of R nabla. What is nabla? It's just a metric Hermitian connection on your M. And here again, you can think R omega like a two form with value this time in end T10 M. Okay, and that is the more difficult part. And you can see from here when alpha prime is 0. Okay, alpha prime 0, just saying that d bar omega is 0. And this is actually the solution, the condition found by Candelas and so on, is the usual Calabi-Yau condition. So the first remark that we can do is, in fact, that the Hall-Strominger system is a generalization of Ricci flat metric on non-Kähler Calabi-Yau, right? Because it's exactly what I say, coupled with the condition with Hermitian Young-Mill equation. And as I say, you can see the Calabi-Yau, let's say, Kähler manifold as a special solution. He just the T10 M bundle, okay? And in this case, you have the two metric coincide. And then this is this thing is exactly the Yau theorem, essentially, okay? Here we have exactly the link with the balance metric. So in fact, we are asking that omega is globally conformally balanced. This is what was not written originally in that way. In the paper by Hall and Strominger was written in this way, asking that this star of omega is in fact E d bar minus E logarithm of the norm of the free zero form, and the equivalent was shown by Li and Yao. So as in the Kähler manifold, you are looking for canonical metrics for metric with some property. Here we are looking, let's say that it's like to consider canonical metric for conformally balanced manifold. And the fact that it's canonical is given by the third equation, which is also called the anomaly cancellation equation that couples the two metrics. And that's a more difficult, the more difficult equation. In the talk, in the rest of the talk, I will essentially consider the case that the nabla is a Chern connection. From physical point of view, this is not, in fact, the right connection. This is a, let's say, nabla equal to the Chern connection is the choice of connection that Fu and Yao chose for constructing the first non-Kähler solution of Hall-Strominger system. From physics point of view, the constant can be any positive, is only positive, okay? But in mathematical literature, you can find also the case when alpha prime is non-zero, in paper by Fong, Picard, and so on. Okay, here I just say a few words if you want really to see the physics situation, okay? You need to impose an extra equation, and that means that your nabla has to be also an instanton. So nabla, let's say our nabla, has to satisfy the equation that I wrote before for F. Okay, for the curvature of the Chern connection. So it's also Yang-Dietz connection. Before to see the solution that we found, I want just to overview something, what is now in the literature about solution. Maybe I forget something for sure. The first solution are found by Fu and Yao, and are torus fibration over K free surfaces. And we will see later that one can generalize that. Instead of considering surfaces, considering orbifolds, but not all K-free orbifolds, but all type of orbifold, let's say with mild singularity, like isolated cyclic singularity. There is a nice construction in the literature on non-Kähler solution only groups and the equation by Fernandez, Ugarte, Villacampa. These are done in this case. You take the real Heisenberg group, quotient by lattice times S1. And here the connection that they use is the Bismuth connection. And then there is also a result by Fei and Yao, where they consider the case of complex parallelizable manifold, so G over gamma, where G is a complex groups. And here they consider any connection of the Gudushow family of Hermitian connection that you can have. And also Granchero gets something else and other people. There is also something related to the duality due to Garcia Fernandez. He constructed a new solution on non-Kähler torus fibration over K-free surfaces, and he found the first example T-dual solution of the Hall-Strominger system. More recently, this is also generalized in the context of G2, but I will not talk about that. Then there are other nice construction, Yu-Fu, Fei, Wang, and Picard, where they consider non-Kähler fibration, where the base is a compact Riemann surfaces homogeneous bigger than or equal to 3, and the fiber is just a compact hyperkähler manifold. Okay, but let's go to our situation. So first I review what Fu and Yao did, and then I will explain a little bit how we generalize that. The way how they construct Fu and Yao the solution is to consider previously the construction by Goldstein and Prushkin, which is in fact a refinement, let's say, of a previous construction by Calabi and Ekman. So let's start with a K-free surfaces with a Kähler-Ricci flat metric, omega s. Now the idea is to construct a tissue bundle in this way. So we choose a pair of 114, which are this time anti-dual, okay, such that the class of omega r are integer. Here often I will forget about the factor 1/2 pi, okay. Anyway, they using essentially connection 1 form on M, theta 1, theta 2, such that you have d theta I equal to the pullback of omega I, they constructing in a natural way the toric fibration, okay? Theta is just the vertical part, let's say, and in a natural way using theta and using omega S, which is a holomorphic 204 on S, they construct a free zero form, just given by the wedge of theta times the pullback of the 204 on M. And the trick here is good if you pullback omega S by the holomorphic reaction, and you add essentially the theta wedge theta bar. In a natural way, you get the balance metric. Okay, so the omega 0 will be co-close. Okay, so the trick is now to modify that. How you modify? You let's say the part involving theta, you leave in the same, so you don't change. And you just change this part. Instead of considering omega S, you multiply omega S for E, the exponential of a scalar function on S. And then the idea here, of course, it's not so easy. I will describe it in an easy way, but is to reduce everything, to the system, to a two-dimensional Monge-Ampère equation with gradient terms, which is of this type. Of course, you have a positivity condition that is given for the metric omega u, which is given by this condition. And f is just a null function, and you have a 2-2 form with average 0 with respect to the metric. That's the things. And the hard part found by Fu and Yao is to show that, in fact, the previous complex Monge-Ampère equation has a solution. Okay. So in this way, they found a solution to the whole Strominger system. Okay. And on the manifold is just a toric fibration over K-free surfaces. I write here again, the connection here that they consider is the Chern connection. And later, this equation was studied in higher dimension by Fong, Picard, and so on. So there are generalizations of this equation. Okay, so let's see what we did. So instead of considering, let's say, K-free surfaces, we consider a K-free orbifold with a Ricci flat Kähler metric, omega S, and let's note by ES, the orbifold Euler number. Okay, all the theory in case of orbifold can be extended. And let's consider again a pair of anti-cell dual form, for which the class are in fact integer class. And what we will consider is a T2 orbifold bundle determined by that. The Chern-Weich theory can be extended in this case in such a way, this is a part of a suctionist mode. And then if we consider a stable vector bundle of degree 0, okay, be careful that the stability depends on the choice of metric. One can here say, okay, this stability is in the Kähler case, then was generalized by Li and Yao for, let's say, in the context of conformally balance. It makes sense also for orbifold. That's orbifold that has, let's say, mild singularity by a paper by Simpson. And then we assume that the C2, the Chern class G2W and the C1 square satisfy exactly this relation. This is very similar what Fu and Yao had. Then just taking the pullback of W, the pullback of the metric, we found a solution of whole Strominger system. In fact, now becomes more harder. At the beginning, we thought, okay, it's easy to find this stable bundle. In fact, it's much more complicated to find stable bundle in the case of K3 orbivore. And in fact, we found we had to modify the paper on arXiv because we found a way to find explicit stable bundle on the orbivore surfaces that we consider using generalization of cell construction. So it's more complicated than what we thought. Anyway, let's see. I give a sketch how we show the result. So the first part is very similar to the Fuyao situation. So we will consider the, let's say, the torus bundle. And again, the metric will be the pullback of omega s plus essentially θ1 wedge θ2, if you write in the real terms. And then the condition to be balanced, so d omega square 0, is exactly equivalent to this condition that omega 1 and omega 2 are both 3-0 with respect to omega s. Then if we choose omega 1 and omega 2 to be harmonic, then essentially we are asking that the cut product of omega s with the class of omega 1 and omega 2 is 0. Okay, that's exactly the topological condition. And what we have, okay, consider a holomorphic Chi0 form on your S. So with constant norm with respect to omega s, then the form, you can just simply take theta wedge omega s, and then you take a holomorphic 3-0 form with constant norm with respect to omega. That's not difficult. So we can now play in the same way. So consider the same, let's say, modification of omega using a scalar function u in the same way. So here it just everything done, just taking the pullback, okay, the pullback of the stable bundle, the pullback of the metric, and the pullback of the curvature. So this is not the difficult parts. Here is the analytic part that is a little bit more difficult, but comes from this remark, okay? Essentially, why is working the Fuyao, let's say, solution or construction depends only on the foliated structure of the manifold. In fact, what we have in our situation, okay, is, let's say, a transverse Calabi-Yau structure. So it means that you have a Riemannian foliation, and the transverse Levi-Civita connection is holonomy contained in SU3. Okay, how is defined this foliation, this Riemannian foliation, which is in fact transverse Calabi-Yau, is defined using zeta, okay, which is the 1-0 vector dual to the 1-0 form theta. So we use the real part of zeta and the imaginary part of zeta. And what we have here, that this omega, small omega b, and big omega b, which are essentially constructed by pullback, are basics form. And they are omega b is closed, omega b wedge d theta is 0. And if you use, this is a part to be basic, in fact, if you contract omega b by zeta, this is 0. And then you have exactly what in the literature is called transverse Calabi-Yau structure. So the other part here now is to consider that, let's say, the third equation on the Hall-Strominger system, and to rewrite that in terms of this data, okay? And what it turns out that, in fact, we success to write that in terms of transversely elliptic equation. You don't have a usual elliptic equation because you have this foliation, but we can show that we have a transversal elliptic equation. And then we solve the equation that we got using a previous result by Tachimi, that is a general result for transverse Calabi-Yau structure, more general, let's say. And that's is success. Yeah, but you say, okay, we did all of this, but we don't see new example for this system. And that's a way how we construct explicit example. So the idea is the following. So our solution will be smooth then. So the idea is the following. We will consider T2 bundle over an orbifold. So we start with S, which is an orbifold, okay? Then we consider, I will call a little bit what it is, a safer S1 bundle, okay, on S, which is not necessarily smooth in general, but we construct in such a way using specific rational divisor, you can construct in a way that M1 is smooth. Okay, so we get something with fiber S1. And then here we have a smooth manifold, so we just take a regular principal S1 bundle over M1. So the way how we construct the solution is starting from our S at the end to have a T2 bundle over our orbifold, which is smooth. I think I have not so many minutes, but I want just to say a little bit about this safer S1 manifold. Let's say all this theory is more or less due to Collar, because the nice thing of this S1 safer bundle, let's say, if the base is Einstein, okay, also the total space, the safer bundle is Einstein. In fact, it was used by Galiski and Boyer-Galiski for Sasaki-Einstein manifold, but we will use in this situation. So the idea is that we have, let's say, roughly speaking, we have a 2n+1 manifold, which emits a differential map of a complex n manifold such that the fiber is circle. And in fact, outside, let's say, the singular point, you have a usual S1 bundle. Roughly speaking, is something like that. And the natural setting is to take the base, our base, will be a complex locally cyclic orbifold. So very simple from the point of view of orbifold, because locally will be a quotient of Cn over G, where G is just a cyclic group. So what the main idea is to consider this union of Y divisor on X, such that essentially, if you remove this union, okay, and you consider your fibration over X, you move in this union, you have just a usual circle bundle. You have to think that the fiber, in fact, are just, let's say, the quotient of C star, you have an action of C star over the group of unit, the root of unit, okay, which will be unit of order M, let's say, and these MI are exactly, let's say, what are the natural multiplicity. I am speaking very roughly about that, just to give an idea. But the nice thing by Collar, that in fact, a safer S1 bundle here, first you work to C star, and you can think essentially you reduce from C star to C1 in natural way, the topologies don't change it. So it's, from that point of view, is okay. And everything is determined by what is called a co-divisor. You see, is a combination. Di are the divisor that I considered before, and Mi are the multiplicity. So you have a rational coefficient in your combination. And the idea is the following, that the safer S1 bundle is uniquely determined by what is called the first chain class, which is given by this. It's essentially given by, here we take Y divisor over X. So we take the, essentially we associate to be the line bundle, the homomorphic line bundle, and then we take the first chain class, okay? That's exactly the class that you can view as a rational class, in fact. And then you have a combination of your class determined by Di, and here what you have is some number, okay, integer number, Bi, which are relatively prime to Mi. So the nice thing here, this picture, is everything is determined. In fact, you can see from here, from a choice of Y divisor and this integer. And then your safer bundle is determined. And what we did essentially in our construction is to choose carefully rational divisor, okay, for essentially to a pair or rational divisor. The type, okay, free, and then I will finish in, can I go over 2 or 3 minutes? Is okay?
Yes, sure.
Okay, so we will start with this explicitly. We apply the construction to a very simple orbifold surfaces in this way. So let's consider the projective space, weighted projective space, okay? And the intersection of 2 degrees 6 hypersurfaces on that, which are in generic position, is a very simple situation. I mean, it's a singularity, but as orbifold is quasi smooth, so it's almost smooth, let's say. And the nice thing here that everything in some sense works, that this type of free orbifold has isolated singularity A1. This is the Duval classification of singularity, but essentially it means that locally you have something like C2 over zeta 2, and then using the blow up of this orbifold at 9 minus k points, we construct a smooth safer S1 bundle over S. Of course, choosing carefully a rational divisor on that. And then just simply taking the product, we obtain a solution of the Hall-Strominger system on M, okay? How we detect that this manifold is Z is exactly this direct sum, the connected sum, sorry, of S2 times S3, is just because we get our manifold is simply connected, dimension 5 with a semi-free S1 action. And then by the topology, you can identify what is, but this is not a simply connected example. We want a simply connected example. So we do something else, more complicated. We need now to choose 2 independent divisor or Q. And so we first construct 1 and then we construct 2. And then again, we identify what it is. And what it is at the end is this connected sum of R copy of S2 times S4, connected sum of R plus 1 copy of S3 cross S3. And these is essentially given by the second cohomology of your manifold. So I finish with the theorem. So what we show that the product of S1 times the connected sum of K copy of S2 times S3, and with K between 13 and 22, that's depend on B2, as I said before. And this connected sum, this is maybe more interested in this K because it's simply connected. We found solution, they admit solution to the Hall-Strominger system, essentially using a generalization of Fuyao construction. And for the biggest K, the biggest R, you get exactly the Fuyao solution. And you can see, I already said before, that they essentially, from geometrical point of view, you have a principal S1 bundle of a smooth, safer S1 bundle. That's, I think I finish here. Sorry that I overtime a little bit. And thank you. I didn't, maybe in the question I can answer today. I can say something about anomaly flow. And thank you very much for your attention.
Thank you very much, Anna. Are there questions? I have some questions that I keep for the
good.
1 hour. Are there questions? Comments or remarks? Okay, maybe we can postpone the session, the question for the special session. So we will resume